Hello everyone. The title of this video is Solve Equations Involving Rational Exponents. So every example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org, and I'm in their Algebra and Trigonometry text, section 2.6, titled Other Types of Equations, and I'm working under the heading Solving Equations Involving Rational Exponents. So each example I'm doing is either an example from the reading, or one of the try it problems from the reading, or one of the exercises at the very end of the section that are related to this particular objective. Now I would request that whenever I bring up a new example, that you pause the video and try to work it out yourself first before watching me doing it and comparing. Because if you're just watching me do these things and not practicing, that's an issue, right? You should be practicing these things and not just watching me do them all the time. Okay? Great. Alright, so all the examples I have written out on paper, and we're asked to solve equations involving rational exponents, right? Fractions for powers, right? Fraction powers, fraction exponents. So we're asked to solve the equation. It says use factoring when necessary. Right? So you're going to see me, I'm going to go through some of these in multiple ways. I'm going to go through some of these questions in multiple ways, and show you that there's more than one way to tackle a lot of these. Now, before we get into this, we have to recall something about rational exponents. So actually a few things. So hopefully you recall from maybe a previous video or previous lessons in other algebra courses or through your reading, that if you take a number, I'm just going to use x because most of these will have the variable x in it, and raise it to a fraction power, right, the m over n power, where m and n are integers and n is not 0. Okay, we can't have a denominator of 0. Remember, there were two different ways to express this. One, you could do using the power to a power property of exponents, we could express this as x to the 1 over n power, and then to the mth power after that. Right, m times 1 over n would be m over n. And if you recall also, x to the 1 over n power is another way to express the nth root of x. So if you want to express these as radicals, this would be the nth root of x in here, to the mth power outside. Or we could do it the other way around, where I switch these powers. If you see a number to a fraction power, right, again, I'll just m over n. I can express this using the power to a power property for exponents as x to the mth power and then to the 1 over n, right? Because 1 over n times m would be m over n. Right? And once again, you see something raised to the 1 over n power. That can be expressed then as an nth root, right, as a radical. So this is equivalent to the nth root of x to the mth power inside. So either one of these is acceptable. right, as long as the roots are able to be taken, right? We're going to be considering finding the real number solutions of these particular equations. Also, something else to consider. One method I'll show you for solving such an equation is to take a number or an expression with a fraction power and raise it to its reciprocal. So x to the m over n, raise that to the reciprocal, n over m, right? Flip the fraction. Right, so now if, right, normally this will be x to the first power, but you really got to be careful. Right, you really have to be careful. Remember the denominator of a power, right? The denominator of a power kind of tells you what roots you're taking. So you could think of this as the mth root of something to the mth power, right? Because m is in the numerator here. So we could actually look at this in one of two ways. It's just x if, m is odd. Right? Maybe you recall this. If you were to take the mth root of x to the mth power, remember this was just x if you were taking an odd root of an odd power, right? Cube root of a cube or fifth root of a fifth power. Right? So maybe I'm hoping you recall something like that, right? It's a little tricky. But if m, right, if the root being taken is even, then it's the absolute value of x. Right, if m is an even number, for example, right, remember the square root of x squared was the absolute value of x, right, not just x, because this root symbol, right, was asking for the principal root, the positive one, not the negative one. Okay, but again, the most important stuff is up top here, right? The different ways of rewriting an expression to a fraction power. You may not need to remember this so much at the bottom here, because we're going to end up checking our solutions anyway at the end. So this may not be as important as I make it out to be. Okay, so my first example. You have x to the 3/2 power equals 125. Now this is one, again, I'm going to show you how to do these in multiple ways. Alright, so there's really no one set way to solve such an equation. Now one way is just to isolate the power, which, there's only one term with a power here. Isolate the exponent, isolate the power, the variable expression to a power, and now I have a variable expression to a power equals 125, equals a constant. And then we could try this out here. I raise both sides to the reciprocal of that power. So for instance here, I have x to the 3/2 on its own side, and then 125 on the other side. Okay, and then I'm, raising both sides to the reciprocal of 3/2, which would be 2/3, right? The 2/3 power. And you'll see, since 2/3 has a denominator that's odd, this would be an odd root of an odd power, kind of. It's kind of like an odd root of an odd power. So this will just be x. And then again, remember you can rewrite 125 to the 2/3 power as the cube root, right? The denominator of the power tells you the root. You could take the cube root of 125 and then raise it to the numerator power, right? This is one way to do it. Because I'd rather not do it the other way, do 125 squared, because that'd be huge, and then take the cube root. Now the cube root of 125 is 5, and 5 squared is 25. Alright, so here's a possible solution. And let's not forget to check this. Always check it back in the original equation. Now, we'd have 25 to the 3/2 power equals 125. Is this true? Now 25 to the 3/2, the denominator is 2 on this power. So I'd be taking the square root of 25 first, which is 5, and then to the 3rd power. We'd have 5 to the 3rd power equals 125, and then that's indeed 125 equals 125. It works. So right now, the only solution I'm finding to this equation is 25. Right, it's 25. Wonderful. Now, as I mentioned, there are alternate ways of solving such an equation, right? Just depending on how you want to look at writing the fractional power. So I could also do this. For example 1 here. I could think of x to the 3/2 as the square root of x cubed. Right, this is the same thing as x to the 3/2 equals 125. Right. And then if we're only looking for real number solutions, right, if we're only looking for real number solutions, no imaginaries, remember the only one number, right? Every number, every real number like 125 only has one real number that you can cube to get it. It's not like an even power. So if we're sticking to the, basically take the cube root of both sides, then the square root of x, then the square root of x must be equal to the cube root of 125, the real cube root, which is 5, and then I would square both sides. Right? Then we would square both sides, get x equals 5 squared, x equals 25. Right? Same thing. Right? Or I could have thought of this as x cubed to the 1/2, or the square root of x cubed, right? Then squared both sides and then took the cube root. And either way, I end up with the same solution I got before. Alright, x equals 25. Alright, now there is another way to try and solve this thing. Now again, I'm gonna emphasize that we're only asked to look for the real number solutions, no imaginaries, but some of these equations could have solutions with an imaginary part. Let's see. Alright, so as I was saying, if I replace, now this is something people very often do in equation solving, make substitutions. If I replace, the square root of x, or x to the 1/2, with, I don't know, some other letter, say u, then this equation becomes u to the 3rd power, right? Because I said earlier, Right, this is the square root of x to the third power. You can think of it that way. And if I replace that square root of x with u, the equation becomes, u to the third power equals 125. And now what I have here is a polynomial equation. There's no fraction powers anymore. There's nice whole number powers. This is a polynomial equation in the variable u, right? Because I'm only seeing u to a whole number power. And you know how you would normally solve polynomial equations, right? You take everything to one side, 0 on the other. So I have u cubed minus 125 equals 0, which this left side is u cubed minus 5 cubed, right? 125 is 5 cubed. And this is factorable. Alright, this is a difference of cubes over here. So when they said, factor when necessary, I mean, the factoring isn't necessary here. We saw how to solve it, without factoring. I'm just saying there are alternate ways to look at things. But this is a difference of cubes, right? So I should be able to factor this. So we'd have, u minus 5 times u squared plus 5u plus 25, right? This is how this would factor, equals 0. And now I have a product equal to 0. So by the zero product property, at least one of these factors has to be 0. So either u minus 5 equals 0, or this u squared plus 5u plus 25 equals 0. And if I solve each of these for u, here I'm getting u equals 5, right? And then over here I can use the quadratic formula. U equals, negative 5 plus or minus, 1 with the plus, the square root of, 25, b squared minus 4ac, 25 minus 100, so negative 75, divided by 2a divided by 2, or, u equals negative 5 minus the square root of negative 75 divided by 2. And again, these numbers here would not be real. Alright, these numbers are not real because of the square roots of negatives. Alright, and again, we're going to focus on just the real solutions. So then I go back to here. This only has a real number involved. And remember what u was, right? U was the square root of x, and I get the square root of x equals 5, squaring both sides. X must be 25, right? Now you could square both. I mean, if you were looking for imaginary solutions, we could try to keep on with these. This would be the square root of x equals, negative 5 plus, and then I would write the square root of negative 75 as, 5 times the square root of 3, right? That's the square root of positive 75 simplified, times I, right? And then divided by 2. And we square both sides of this, square the numerator, square the denominator. Let's see, if let's square both sides of this, and then I'm going to use a calculator to check this. Numerator, you got 25, and then minus 25 times the square root of 3 times I, but twice, so minus 50 times the square root of 3 times I, and then plus, 75I squared, but remember I squared is negative 1, and then all divided by 4. So 25, minus 75, that'd be negative 50. And then minus 50 times the square root of 3 times I, and then divided by 4. And if we divide each of these by 4, so one possible solution is negative 25 halves minus 25 halves times the square root of 3 times I, right, if I write it in standard form for a complex number. Now I'm going to check this. I'm going to check this by using a calculator. Right. So I'll pull up a calculator here. Now I have a TI-84 plus, and I'm in this complex mode. Right, A plus BI mode here, not real mode. Let's see what happens when I go back to the original equation and plug in this complex number, right? X to the 3 halves equals 125. So we get, let's see, I'm going to take in parentheses, right, negative 25 halves minus 25 halves times the square root of 3 and then times I, and then that's being raised to the 3 halves power. And see what we get. And look now, it's negative 125, right? So this is not a solution, right? And like I said, we're only going to be focusing on finding the real solutions to this. But this ends up being negative 125, right? Not positive 125. Well, let's see what, I mean, if I multiply these by negative 1, let me just re-enter this and change these minuses to plus. Just curious what happens here. This would be 125i. Right. And just one more little. I'm pretty sure this won't work. Well, if I change that to plus, that'll just be the other solution. Yeah, it's negative 125. Right. Okay, so not getting any solutions from that. But either way, right? Not getting any solutions, any good solutions from that. But yeah, no matter how you check it though, right? Again, we're only going to be focusing on the real solutions only. Right? I said that at the top of the video. I've said that a couple times here. So if you ever come across, for some reason, the square root of a negative, we're going to ignore it for now, right? With these equations involving rational exponents. All right, yeah. So this, I would not recommend doing this way here. Just this first way I did it, or the second way I did it, where you wrote it this way. I would recommend doing those things ahead of that last convoluted way I did it. So yeah, isolate a power, raise both sides to reciprocal power, and check your solutions, or write it in one of these two ways, and then eventually raise both sides to some powers and whatnot to get the variable alone. Right, so again, sorry about that third way, right? Bringing in imaginary numbers. I'm sorry about that. But we're going to focus on the real solutions only. Alright. So example 2. Right, pretty similar. See, I've got a variable expression to a power all by itself equals, a constant. So we could, raise both sides to the reciprocal power. So I have x plus 5 halves to the x plus 5 to the 3 halves, and I raise this to the 2/3 power, and then do the same thing over here, 8, and raise it to the 2/3 power. All right, and then because this denominator is odd, this will just become x plus 5 to the first power. And then 8 to the 2/3. The denominator is 3. So you're taking the cube root of 8 first, which is 2, and then squared is 4. And then I would solve for x here, subtract 5, x equals 4 minus 5 is negative 1. And then don't forget to check this. And again, I'll check it by hand here. When I plug in negative 1 for x, you'll have 4 to the 3 halves on the left side. Is this equal to 8? Well, the square root of 4 is 2. 2 cubed is 8. We get 8 equals 8. Check. All right, so x equals negative 1 is the valid solution, the real number solution to this equation. All right. Great. Now, once again, you could have also done the following, thought of this as the square root of x plus 5 to the third power. And then said this is equal to 8. And then there's only one real number that you can cube to get a number. Every real number has one real number cube root. So the square root of x plus 5, must be equal to 2, right? The cube root of 8. And then squaring both sides, we get x plus 5 equals 2 squared, which is 4, and then we get the same stuff, right? Subtracting 5 from both sides, x equals negative 1, you check it out, it works. All right, so the solution I'm getting there, the real number solution, there may be imaginary solutions, but we're not going to worry about that. All right, solution is negative 1. Okay, now this one, see x to the 2/3 equals 16. This one's going to be a bit trickier. All right, this one's going to be a bit trickier because of this, right? So left side, now if I do the reciprocal power thing, raise both sides to the 3 halves power, and then over here we have 16 to the 3 halves power. See, this denominator on the power I just raised both sides to is even denominator, right? 2. So this is like taking the square root of an even power. So this should actually end up being, instead of x, should be the absolute value of x equals, and then over here, square root of 16 is 4, 4 cubed is 64. All right. And then what numbers, now absolute value, remember on a number line, is just the distance from 0. So what numbers have an absolute value of 64? We get x could be positive 64, right? The absolute value of positive 64 is 64, or x equals negative 64, right? The absolute value of negative 64 is also 64. So I get 2 possible solutions here. Now, we must check them, right? So x equals, 64. Let's see. We have 64 to the 2/3 power. Would this be equal to 16? Right, so remember how this works. You take the cube root of 64 first, which would be 4, and then 4 squared equals 16. That's 16 equals 16. That works. So 64 is a valid solution. Now check x equals negative 64. Right now, don't forget parentheses around negatives when you replace them. Right, this would be negative 64 to the 2/3 power. Is this equal to 16? Remember, you're taking the cube root of negative 64, which would be negative 4. Right, negative 4 to the 3rd power is 64, and then you're squaring that. And negative 4 to the 2nd power is positive 16. So this equation actually has 2 solutions, positive 64 and negative 64. Right? Both of these work. And again, you can check these with a calculator if you wish as well. But 2 solutions, right? So yeah, that's the trick. That's a tricky part. Right? When you raise to some fraction power, a fraction to a fraction here, and that fraction you're raising to has an even denominator, you're getting the absolute value of the base and not just the base. Now, if you don't like remembering that, Remember, you could always do it this way as well. This is the same, x to the 2/3 is the same as the cube root of x squared, right? And then we have equals, 16. And then you could apply that square root property. Right? We've seen this with quadratic equations. There are certain equations you can apply the square root property to. If you have an expression squared equal to a number, well, then the number being squared, the expression, that cube root of x, is either equal to the positive square root of that number, positive 4, or, another number that you can square to get 16 is negative 4. So this cube root of x could be equal to negative 4 as well. And then solving each of these, you'd raise both sides to the third power, right, to get rid of the cube root. So x would be 4 to the third power, which would be 64, or x is, negative 4 to the third power, which is negative 64. And these are the exact same solutions I got earlier. Okay, but it does have two solutions, 64 and negative 64, two real solutions, right? It may have an imaginary number solution, but I'm not going to try to find it if it does. Right? We're only going to focus on, again, the real number solutions here. All right. Now the next example will involve factoring because there are multiple terms with a power, right? Multiple terms with a power, right? Multiple terms with a variable, a variable expression to a power. So multiple terms with variable expression to a power, right, or just variable expression. We're going to try factoring, right? Factoring may be involved here. Or I'll say try factoring. Remember how you solve most equations by factoring. You take everything to one side, 0 on the other, which this already has. And then you factor out. Now, there was in an earlier section of this text on factoring in chapter 2, there was a part of one section on factoring expressions with rational exponents like this. And you pull out, the greatest common factor, which, both of these have a power of x in it. So the greatest common factor is going to have a power of x, and then the power on that power of x is the lowest power of x. Now this term has x to the half. This term has x to the 1/4. 1/4 is smaller than a half, right? So I'm going to factor out, x to the 1/4 power times, and then you just kind of divide each of these terms by x to the 1/4 power to see what would be left over. Now x to the 1/2 divided by x to the 1/4 would be x to the 1/4. So we have 2 times x to the 1/4. Right, and if you were to multiply these, you'd have 2x to the half, right? You add the powers, get x to the 2/4. Minus 1, right? X to the 1/4 divided by x to the 1/4 would just be, you just have 1 left over. So this factors nicely to, x to the 1/4 times the quantity, 2x to the 1/4 minus 1. All right, and now I have a product, multiplication here, our product equal to 0. So by the zero product property, the only way a product of real numbers is going to be equal to 0 is if one of the factors is 0. So either x to the 1/4 equals 0, or this other factor, 2x to the 1/4 minus 1 equals 0. And then we're solving each of these, which I'll go over here and do. Now the first one's no problem. There's only one number that when raised to any power is 0, and that's 0, right? Or you could raise both sides to the 4th power, but you're seeing x equals 0. There's one possible solution. Or, and then here I have an equation like my first 3 equations, where there's only one term with a power. So I'm going to want to isolate that. Right, this x to the 1/4, right? Now that that's the only power, let's isolate it. So I'd be adding 1 and then dividing by 2. We get x to the 1/4 power would be equal to, 1/2, positive 1/2. Remember, this is the same thing as the 4th root. And I would raise both sides to the 4th power here. Get x equals, 1/2 to the 4th would be 1/16. So I get two possible solutions here. Now let's check them. All right, let's check them. Well, when x equals 0, you have 2 times, 0 to the 1/2 minus 0 to the 1/4 equals 0. This left side is definitely 0. We have 0 equals 0 for sure, right? Because 0 to any non-zero power is 0. So you'd have 0 minus 0 equals 0. So this works. 0 is a solution of this equation. And then when x equals 1/16, we'd have 2 times, 1/16 to the half, which is the square root of 1/16, the principal square root, minus, and then 1/16 to the 1/4 power, right, which is like the 4th root, right, the principal 4th root of 1/16. So this would be 2 times 1/4, right, that's the square root of 1/16, the principal square root, minus, and then the principal 4th root of 1/16, as we saw up here, would be just 1/2. And then we get 2 times a 4th, that's a half, minus a half equals 0. That's totally true. You get 0 equals 0. That also works. All right, so once again, we have an equation with two solutions. Two real solutions, right? 0 and 1/16 both make that original statement true. Okay, wonderful. All right, so now this next one doesn't have multiple terms with a variable to a power, so there's no need for trying to factor here. This example is just like examples 1 through 3, where I can raise both sides to the 3 halves. Right? So we have x plus 1 to the 2/3, right? And then I'm raising it to the reciprocal power, right? Raising it to the 3 halves, and this is another one where you got to be careful. Because raising to the 3 halves, I'm saying, oh, this is an even denominator. So it's like taking the even root of an even power. So this ends up being the absolute value of the base, not just the base. And then the other side, I got 4 to the 3 halves power. And like I said, this side will be the absolute value of x plus 1, not just x plus 1, because of that even denominator, the even root of an even power that I'm taking here. And then 4 to the 3 halves, the square root of 4 is 2, 2 to the 3rd power is 8, 4 to the 3 halves is 8. All right, and then we just have to think of, what numbers have an absolute value of 8? Well, 8 or negative 8. So this expression inside, right, this number inside the absolute value symbol can either be 8 or negative 8, and then I solve these, subtracting 1 from both sides. Here we get x equals 7 or x equals negative 9, and don't forget to check them back in the original equation. Again, I'll do these out loud. When I plug in 7, 7 plus 1 is 8. And 8 to the 2/3, right, would be the cube root of 8, which is 2, squared is 4. You get 4. You would get 4 equals 4. So 7 works. Plugging in negative 9, right? Negative 9 plus 1 is negative 8. Negative 8 to the 2/3, right? You're taking the cube root of negative 8, which is negative 2, but then squaring it, which would be positive 4. This also works. So yet another equation with two real solutions, positive 7 and negative 9. All right, and then once again, you could also think of this, right? I'll do this one more way too, right? Just like I did with the other ones. You could think of this as the cube root of x plus 1 squared equals 4. And then apply that square root property, right? What squared is 4? Well, that thing that's being squared, right, the cube root of x plus 1, could be positive 2, right? 2 squared is 4. Or the cube root of x plus 1 could also be negative 2, right? Since negative 2 squared is also 4. Then cubing both sides, we get x plus 1 equals, 2 cubed is 8. Or here, cubing both sides, x plus 1 equals negative 2 cubed, which would be negative 8. And then I get the same exact stuff that I got over there, right? You get 7 and negative 9 as possible solutions. And when you check both of those, they both end up making the original statement true. Great. All right, and I've got just one more example. Now this one is just like example 4, where there are multiple terms with a variable expression to a power, right? There are actually 3 terms here with a variable to a power. So I'm going to try factoring, right? Because I see that there are multiple terms with that variable to a power. I'm going to try, solving this by factoring. And remember how you, try to solve equations by factoring. You get every term to one side, 0 on the other, which is already the case here. Then the greatest common factor, the expression I'd be pulling out of these 3 terms. Now notice they all have x to a power. Right? Every single one of these 3 terms has x to some power. So I'm going to pull out, x to some power, and it'll be the lowest power on any of these terms. 7/3, 4/3, 1/3. 1/3 is the lowest of those. So I'm going to factor out x to the 1/3 power. And then if the other factor will be what's left over when I remove x to the 1/3. So basically just subtract 1/3 from all these powers, right? You're dividing each of these by x to the 1/3. So you have x to the 6/3, which would be x squared, right? Minus 3 times x to the 3/3, which is just x to the first. And then minus 4 times, x to the 0, which is just 1, right? So minus 4. All right, and we have equals 0 still, and now I have x to the 1/3 as one factor, and then x squared minus 3x minus 4, a quadratic polynomial, as the other factor. And this can actually factor even further if you wish, right? So this is x to the 1/3 times, and then this, right, x squared minus 3x minus 4, this would factor to x minus 4 times x plus 1. We have equals 0. And now I have factored both sides as far as I can. And now I'm going to apply the 0 product property. By the 0 product property, the only way a product is equal to 0 is if one of the factors is 0. So either x to the 1/3 equals 0, or this second factor, x minus 4, equals 0, or this third factor, x plus 1 equals 0. Solving each of these, now the first one, is simple enough. You would cube both sides, and it's just x equals 0, right? The only number that you can raise to any non-zero power and get 0 is 0. Or here I'm adding 4 to both sides to get x equals 4. Here I'm subtracting 1 from both sides, x equals negative 1, and don't forget to check your solutions. Now, 0 should be obvious. You'd have 0 minus 0 minus 0 equals 0. So there we go, right? This is obvious. Now 4 is not as obvious, right? What's 4 to the 7/3 power? That's not a very nice number, right? Because the cube root of 4 isn't nice. And the same thing with 4 to the 4/3 power, 4 to the 1/3 power. But if you look at it in factored form, right, these are actually equivalent. You'd have 4 to the 1/3, and then here you'd have 16 minus 12 minus 4, that's 0. This factor would be 0. This would end up giving you 0 equals 0. Right? And I'll go to a calculator and doubly verify this. Same thing for negative 1. Now the nice thing is negative 1 to any power is pretty simple. Negative 1 to the 7th third, the cube root of negative 1 is negative 1. Negative 1 to the 7th power is negative 1. So you have negative 1 here. Negative 1 to the 4th thirds power would be positive 1. Right? Cube root of negative 1 is negative 1, but to the 4th power would be positive 1. So you have negative 1 here, then minus 3 times 1, so negative 4. And then, negative 1 to the 1/3 is negative 1 times negative 4 is positive 4. You have negative 4 plus 4 equals 0, right? That totally works. And again, I'm sorry I spoke very quickly there, did all that out loud. Now, again, if you'd like to check, with technology, you can. And I'll show you how I do that. Right? So let me go back to real mode. I'm in the A plus BI mode, as I showed you earlier in the video. Let me go back to real mode, because I really only want to deal with real numbers here. And I'm not checking 0. Right? So let me check 4. So what I'm going to do is I'm going to hit the number 4, and I'm going to store it as x. Right? So now every time I hit the letter x, it's the number 4. And I'll just enter this expression that's on the left side here, and hopefully we get 0. So x, raised to the 7/3 power minus 3 times x, which is 4, right, raised to the 4/3 power, and then minus 4 times x, which is again 4, raised to the 1/3 power, and hopefully this gives me 0. And look at that, it does. Hooray. So 4 works, and I leave it to you to check negative 1 in the same fashion, using some sort of technology if you wish. But yeah, so here we have an equation with 3 solutions. Great. All right, so again, from that, going back to that first example, with these rational exponent equations for this particular text, we're only asked to find the real number solutions. So yeah, if you ever come across square roots of negatives like I did with that weird alternate way I tried solving example 1, just ignore those for now. Only focus on finding the real number solutions in the way that I found for all these 6 examples here. Alright, so I'm hoping that watching me go through these 6 examples and check, please remember to check your solutions at the end. That's always important when you're solving equations. But yeah, I'm hoping that watching me go through these 6 examples helps you in some way when you're asked to solve an equation involving rational exponents on your own. And thank you very much for watching.